Okay, so now that we have some general understanding of what a confidence interval is, and we've had some practice at constructing a one sample t interval for a mean, let's look at some properties of a confidence interval. Now, this is very similar to what we saw for a one sample proportion interval, and really any confidence interval, these three topics will apply. Let's go ahead and look at the following scenario here. The Financial Aid Office wishes to estimate the cost of textbooks per quarter for students at Milton University. The Financial Aid Office is pretty sure that the amount of money spent on books by all students varies widely, and that a reasonable value for mu is $550, and for sigma is $150. A random sample of 1,000 students were surveyed. So assume the conditions for inference are met, and we're asked to construct different confidence level of intervals. We're asked to construct a different sample size, and etc. So let me give you a few moments. Go ahead and type these fancy values into your handy dandy calculator, and then we'll come back whole group to check our answers and to stamp the properties. Okay, so hopefully your intervals look similar to mine, and if they don't, maybe there was a typo in the calculator or a typo in your inputs. But all good, these are the results I obtained, and notice I am including some context for these intervals, because again, proportions were giving us percentages of the data, and now we actually have quantitative values that represent these specific intervals. So I notice here at 90% confidence, my interval is a little bit shorter than at 95% confidence. So we'll stamp that. And also, if I keep 90% confidence, but I increase the sample size, my interval shrinks. And if I keep 95% confidence, but I increase the sample size, my interval also shrinks. So we have a few properties here, and really we're just going to pay attention to the first two. But the higher the confidence level, the wider the confidence interval. The higher the sample size, the smaller or more narrow the interval. And this one is a special case, meaning it's very unlikely that you're able to change the sample standard deviation, because when you think about it, here's our margin of error. Mathematically, yes, T star and S would be directly proportional as one increases, so would the other, whereas N here would be inversely proportional to the interval. So if at all possible, if you're able to change the sample standard deviation by some mumbo jumbo, if you increase it, then this would also increase the interval here, because you are essentially also increasing the scale factor by which you're multiplying. Now, I would not worry too much about this last one, so let's just make sure that we focus on these top two intervals here. Now, the bound of error of estimation, or margin of error, is a critical value times the statistic standard deviation, here, the mean, or what I typically just call capital E. The margin of error tells us how far away the estimate x bar can be from the actual value of mu. Well, this value is used to determine the sample size necessary for which a particular bound on the error is achieved. To determine our sample size, we'll have to solve the equation for n. However, since we're using the t-distribution, this becomes very tricky because we would need to know the sample size in order to use a t-star. Because remember, t-star is built off of these degrees of freedom, which is based on the sample size. So to resolve this, we're going to make a few assumptions and checks for normality. So if any of the three conditions is satisfied, we can use z star since we assume we know sigma. But really, we're going to use the claimed sigma value, and then we're going to use z star assuming that we know in the long run average that eventually it would have a higher degree of freedom and approach that close normality check there. So anywhere we see normality, z is okay. Now, in the margin of error formula, it looks something like this. We have, and I'm going to just leave it as t sigma over the square root of n equals our margin of error. So I can actually swap the places here. I'm actually going to rewrite this as t sigma square root of n equals the margin of error. I'm going to swap the places here such that t sigma, and I'm sorry, who keeps letting me say t? We're assuming z. See, this is why it's hard teaching into an empty, the void. So here's z sigma, and then now I've flopped it with the margin of error and the square root of n. And to resolve this square root, we are going to square both sides. So here, n really equals z times sigma over the margin of error, all of this squared. So we're going to use this formula to find our necessary sample size. And just as a reminder, we're going to use the ceiling function here. So if we obtain a decimal for our answer, we're going to round up to the next value so that we can overestimate instead of underestimating and then potentially violating our margin of error here. So this handy-dandy formula is not provided on the AP Statistics formula sheet, but we can use it to find the sample size. So here, for the estimate to be useful, the margin of error should be within $20 of the true population mean. How large of a sample should be used to be 95% confident of achieving this level of accuracy? So for this case here, I'm going to use the following. I know that z with 95% confidence is 1.96, and in case you don't have that memorized yet, all good. Here at 95% confidence, assuming a z distribution, the critical value is 1.96. The population sigma was given to us as $150, or so they believe. And then lastly, we want a margin of error to be within $20. So we're going to use our handy-dandy formula here. So I'm going to take 1.96 times my sigma divided by my margin of error, and I'm going to square that. And I get 216.09, which means we would need to sample 217 students, because in the context of this question, I can't have 0.09 students. So that would just be a typical response there. This has shown up in the FRQ portion, but more commonly will show up in the multiple choice section. Now, suppose we were to change the confidence level from 95% to 90%. Well, what would happen to our confidence interval? We know that when we decrease the confidence level, the interval would shorten. And what would happen to the needed sample size? Well, I don't know. Let's check it out. So now I'm using a z of 0.90. And again, if you don't have it memorized, I go here to 90%. It looks like it's going to be 1.645. And I'll just take my handy-dandy formula here, and it looks like I've got 1.645 times the 150 all over this margin of error of 20, square that, get some of this magic right here, 152.21, and it looks like I would need to sample now 153 students. And let me box that up for us. So we see here, using the same parameters, except for a different level of confidence, higher confidence needs a higher sample size, lower confidence, lower sample size. And again, remembering that as we increase the sample size, the interval narrows, as well as if we change the confidence level, well, it shifts in whichever direction you're changing your confidence level. But overall, larger samples tend to have less variability, whereas smaller samples typically have more variability. And we can see that here because of this relationship with n in the margin of error formula. Okay, so now let's suppose that the average age of a first-time mother in the U.S. is 26 years. If we wish to estimate the mean age of a woman who, when she gave birth to her first child within 9 months with 95% confidence, how many sample entries should there be if sigma here is 5.8? So here, let us take a look. This shouldn't be too bad, right? If we're using 95% confidence, I'm going to use the value of 1.96. It appears as though I already have my sigma. And where they're trying to trick you here is that within 9 months, but our context here is within years. So our error here, 9 months out of 1 year is going to be 0.75 years. So that's just your math teachers being mean. That's not really the AP test. It could happen. So as always, ensure that you're reading your units. So what would the sample size be that we need? So I'll take 1.96 times 5.8 divided by 0.75. We'll square that and get something like 229.74, which means I'm going to need to sample 230 women. Of course, always try and include context to your answers. This is statistics. We're pretty reasonable. Now, if the confidence level was changed from 95% to 99, I will go here to my handy dandy formula sheet. 99% is 2.576. If I decided to change that, so now is that's a box. Whoopsies. All right. So if I decide to change to 99%, that's going to be 2.576. Again, I think you get the idea here. So you would take all of that, and just to check your work here, you should end up with 394.08, which would lead us to sample 395 women. More confidence that this is closer to the truth. We'll have more women in our sample, higher sample size, less variability in the sample because we have more confidence. So we're getting closer. We've got that low bias, low variability situation that we talked about back in the sampling distributions for a mean. And last example for the day. A set of experimental animals is fed a certain type of grain for 7-week periods to estimate average weight gain. What sample size would be needed if you want to estimate the mean weight gain to be within 10 ounces of the correct mu with 99% confidence? It is estimated from past experiences that the standard deviation is about 1.5 pounds. So, again, let's always define our known. Standard deviation here is 1.5 pounds. A critical value of 99% confidence is going to be 2.576. And just to check my work here, let's see, 99, 2.576, good to go. Another tricky question here, my margin of error is in ounces, but I'm in pounds, and it looks as though 10 ounces out of 16 ounces would give us 0.625 pounds. We got to make sure all of the units cancel out here, and I know the physics teachers will appreciate that shout out there. So 2.576 times our 1.5 all over 0.625. We're going to square that bad boy and get a sample size of about 38.22, but that does not make sense in the context of this question. So I'm going to want to sample about 39 animals for this case here. Okay, why is it going to turn into red? Let's see. Oh, red box. There you go. Okay, so hopefully you feel a little bit more comfortable finding a sample size and then also being asked ways that manipulating the formula for your margin of error changes your interval. So if you need any further practice, go ahead and look in the module or just Google one sample t interval sample size practice. Plenty of resources have that available. So that will conclude our study of one sample t intervals for a mean. In the next lesson, we're going to start talking about a one sample t-test for a population mean. So now we're going from estimating the population parameter to seeing if we have statistically significant evidence towards our alternative hypothesis.